All right, so like we said, we're going to talk about the equilibrium series, starting with the first chapter, chapter 13, which is the chapter dealing with the basics of equilibrium. We're going to start by motivating why study equilibrium in the first place. Then we're going to talk about equilibrium in a qualitative manner, just, in words. And then we're going to move on to some simple calculations, so the quantitative part of equilibrium. The first, say, 80% of the chapter is about reaching equilibrium. Reaching, you might say, the first equilibrium. Okay? Let me adjust something here real quick. Reaching the first equilibrium. Okay. I don't know where this is clipping. It shouldn't. Oh, hello. Okay, this is perfect. Yes, so the first 80% of the chapter is about reaching that equilibrium. And then in the last 20% of the chapter, we'll discuss, suppose we reach an equilibrium, and now we want to mess with it somehow. Okay? How do we figure out where the new equilibrium lies? Whether it lies so-called to the right or to the left. Okay? So let's begin by talking about how to reach a single equilibrium. But first of all, what is this equilibrium business? Imagine a spectrum where on the left-hand side you have all reactants, no products, and on the right-hand side you have all products, no reactants. Right? These are the two extremes that can be possible. Clearly, when your reaction begins, you're here, you're all reactants, right? Because the product hasn't formed yet, the reaction hasn't started. But if you let the reaction proceed, no reaction ever reaches all products. It never goes all the way on this side. That's the essence of equilibrium. Okay? So when you let any reaction in the world run, it settles with some proportion of the reactants remaining and some proportion of the product formed. It settles somewhere in between. Wherever it settles, that sweet spot between reactants and products, that's what we call equilibrium. That's what equilibrium is. It's that sweet spot between reactants and products. Now, why does this happen? Because every reaction is what's called reversible. Let's start with an example. Suppose nitrogen reacts with 3 hydrogens to form 2 ammonia. Right? By the way, that's the symbol for a reversible reaction. Now that you see the symbol, the explanation will seem obvious. It's a reaction that can proceed in both directions, can go forward and backwards. Okay? Now, technically, every reaction in the world is reversible because it can go in both ways, depending on the conditions. Okay? The forward direction, that's the forward direction to the right, and this is the reverse direction to the left. Forward reaction, backward reaction. For any chemical system, these two reactions, these two opposing chemical reactions are always happening simultaneously. They never stop. They're constantly happening. Okay? If you start out here, the forward reaction dominates. Okay? When you start with all reactants, there's only forward reaction, no backward reactions. When you get here, this is still before equilibrium, so the forward reaction dominates and the backward reaction is small. That's why the reaction keeps moving forward, because the forward reaction keeps winning. If you somehow end up here, then the backward reaction dominates. Okay? And so the reaction starts moving back. At the sweet spot, what do you think happens? It never stops. The forward reaction and the backward reaction always happen forever. It's just that they happen at the same rate, happening at the same speed. Okay? So at equilibrium, what happens in terms of forward and backward reactions is that the rate of the forward reaction is the same, becomes the same as the rate of the backward reaction. Yes?
Question. So if we start with all reactions, is it possible for like the backward reaction to ever get become higher than the forward reaction? Does it stop at equilibrium or does it continue going at a certain point and then it goes back and back to the equilibrium?
So it sort of decays. You know how a pendulum swings, right? The equilibrium is at the bottom. Yeah, so for a pendulum, the equilibrium is at the bottom, right? If I start an equilibrium, not an equilibrium, if I start swinging a pendulum in the real world with friction, with air resistance involved, right? It keeps going on, but then it eventually settles on, right? It like overshoots the mark this way, that way, this way, that way, and then it eventually settles there.
So it does overshoot though.
Yes. So when you start a chemical reaction, it'll go like this. If this is where the equilibrium is, it will oscillate and then decay to the equilibrium value. That's what happens, yeah. But unlike a pendulum has what's called a static equilibrium because it comes to an actual stop. It's not moving forward and backward, right? At equilibrium, a pendulum comes to a stop. At equilibrium, the reaction hasn't come to a stop. It's still reacting in both directions. It's just that because it's reacting in both directions at the same speed, you can't perceive a change, right? It's like perceptually in equilibrium. Although in theory, there's reactions still going on, but they're happening at the same rate. Because of this, we distinguish chemical equilibria by calling it dynamic equilibrium. Okay, so that's the theory of it. Great, so that's why it's important to study equilibrium. We're interested in figuring out where exactly is this sweet spot. Okay, that's the one sentence summary of this chapter and the two chapters that come after this. The relationship between this chapter and the next two is as follows. In this chapter, you study the basics of equilibrium. In the next two chapters, you apply these basics that you have studied to two particular contexts, right? So equilibrium relates to chemical systems, chemical reactions. Based on the type of chemical reactions that we encounter, we can go down and start applying them separately. So if your chemical system is an acid-base reaction, that's chapter 14. If your chemical system is dissolution, dissolving something versus precipitating, that's chapter 15, part 1. If it is something called complex formation, it's a separate type of chemical reaction, that's chapter 15, part 2. You see? So the next two chapters are just equilibrium applied to particular types of chemical reactions. But they're all the same. Okay, so that's what it looks like. Now, going back to that spectrum again, and say this is where the equilibrium is, reactants, products, we can put a number on where the reaction stands on this spectrum, right? So now we're moving to the quantitative part of this. We can put a number as to where on this spectrum the reaction lies. You put a number by calculating this expression. This is called reaction quotient. It simply tells you where you lie on that spectrum. Okay? And the reaction quotient, denoted by Q, is expressed as follows. I shouldn't have erased that chemical reaction. Let me put it back. It's products over reactants. It's a fraction, okay? Products go on top, reactants go on the bottom, and everything gets raised to its respective coefficient. Coefficients become powers. Products over reactants, coefficients become powers. So there are two types of reaction quotients, depending on what you're using to measure the abundance of each species in your chemical system. You can do two things. You can either do molarities, also called concentrations, so that's QC, that's concentration reaction quotient, or you can do pressure QP. But they're both the same thing. Products on top, reactants on the bottom, coefficients become powers. So looking at that example thing over there, the product is NH3. Remember from the last chapter, we write molarity in square brackets? That continues here. So it's square brackets, molarity of NH3. Coefficient of NH3 in that example is 2, so the 2 becomes power. Reactants go on the bottom, and the coefficients become powers. Okay. If you want to write the same thing in pressure terms, the pressure of NH3 is denoted by P sub NH3, just notation, but it's the same idea. Products on top, this time we're doing pressure, so pressure of NH3 to the power of 2 divided by pressure of N2 to the power of 1 times the pressure of H2 to the power of 3. Same thing, right? Okay. So there's two types. Think of the reaction quotient as a number that changes with where you are on the spectrum, okay? So the Q value here will be different from the Q value here, will be different from the Q value here. When the reaction reaches equilibrium, the Q calculated at equilibrium, so put equilibrium concentrations or equilibrium pressures into the expression, the Q value, the reaction quotient value that you get at equilibrium is called K, reaction constant. Okay? So in one sentence, Q at equilibrium is K. And just like you have QC and QP, concentration versus pressure, you have KC and KP. Okay? So if I replace these Q's with K's, all I'm doing is I'm inputting the equilibrium values. So you can think of this as sort of the formula, if you will, for the reaction constant. It's just the same thing at equilibrium. And then this becomes reaction constant. What's amazing about the reaction constant is every chemical system, give me some chemical system, it will have a particular K value attached to it. No matter how much reactants you have, no matter how big your container is, no matter, whatever. If you give me a chemical system and a set of like temperature, pressure values, ambient pressure, ambient temperature, so for any given chemical system and any given environmental conditions, the reaction will always go to equilibrium so that this value comes out to be the same. You know what's going on here? So for example, let me illustrate this with, these are all gases, right? Let me take a tiny container and fill it with only nitrogen. Let me fill this with only nitrogen and hydrogen. Okay? Only nitrogen and hydrogen, and maintain the temperature and pressure to be something. And suppose this is 10 liters volume. I put it in, I let the reaction happen, and then I calculate the reaction quotient at equilibrium. It will have some value, right? At equilibrium, Q will come to some value. Let's call that Q1 because this is our first setup. Let me take the same thing, make it bigger, 50 liters, same temperature, same pressure, and fill this up with nitrogen, hydrogen, and ammonia. Okay? Both are the same chemical systems because they have the same chemical reaction going within, and the external setup is the same. The pressure and the temperature is the same. I've just changed the, I guess, the shape or the volume of the container, and I calculate the Q value here at equilibrium. They will be the same. Even though I have different reactants, different species from the same chemical system, here I have different species. Maybe here I have 2 ATMs of that, 3 ATMs of this, 1 of this, 2 of this, 4 of that. No matter what I start with, it will go to equilibrium in the same manner. It will go to equilibrium so that this ratio comes out to be the same each time. Okay, that's what's special about this number. Does that make sense? Okay, so that's the big idea. Great. Yeah?
For the first one,
Uh-huh.
you put N2 and H2, and the second one you put N2, H2, and H2.
Yep. So this is like, I've put two pressure units of N2, 3 pressure units of H2, and 0 pressure units of NH3. Yeah. Yeah. So what's going to happen is this is basically me starting the reaction all the way here, right? All reactants, no products. And it will reach the equilibrium. So the big idea is no matter where you start on the spectrum, you will always reach the same equilibrium, right? Equilibrium doesn't depend on starting conditions. In one sense. In another sense, it does. So if I start here, it will still reach here. If I start here, reach there, and so on. Equilibrium is a unique spot. Okay. Given all that, let's talk about the relationship between Q and K, relatively speaking. If we compare their values, so 3 things can happen, right? Suppose you have a chemical system and you know that the constant, the equilibrium constant for the chemical system is K. You take your chemical system and you calculate its Q value so that your chemical system is not at equilibrium yet, right? So when you calculate Q, it doesn't match K. So 2 things can happen. Your Q value can come to be less than K, or your Q value can come to be more than K. And obviously, if you are at equilibrium, then Q is the same as K. Yeah? K is pre-given to you. It's a calculated value. Someone did the experiment. You have the K value. You have a new setup, and at a given instant, you calculate Q, three things can happen. If Q is less than K, what that means is you're here, somewhere here. You're behind the equilibrium. So the reaction will proceed forwards. So the reaction will go in the forward direction to reach equilibrium. Not forever, but from that point, it will go forward to some extent. And if Q is if Q is greater than K, then you're here. Reaction will go backwards to achieve equilibrium. And if Q equals K, then the reaction is already at equilibrium. Okay, so comparing the values of Q and K allows you to predict which way equilibrium lies, whether it's forward or backwards. Great. Okay. That's all the qualitative. Oh, there's one more thing. Based on the type of chemical system, by the way, equilibrium, the same thing applies not only to chemical systems, but also to nuclear systems, where nuclear reactions are taking place. Also applies to physical systems. For example, dissolution is a physical process, right? Dissolution and precipitation, physical processes, well, roughly speaking. Melting, boiling, also physical properties, physical processes. So all of those have equilibrium. In fact, every process in the world is an equilibrium process, generally speaking. Okay? But because this is chemistry, we're focusing only on the chemical contexts. Great. There's that. Now, there's only a couple possible questions given what we have studied. So that's basically all. That's all the equations you need for this chapter. The rest of this is reasoning. Okay? There's three possible questions you can have. The first one is you're given the concentration values and you're asked to find Q, or the reverse. No, just that. Yeah. Or you're given Q and some concentrations, but it's missing another concentration that you need to figure out. That's one possible question. Another one is you're given the equilibrium concentrations and you're asked to calculate K, or you're given the K value and some concentrations, but you're missing one of the concentrations. And the last part, which we'll spend a fair amount of time on, is you have the K value given to you, and you have the initial concentrations given to you. You want to figure out the equilibrium concentrations. The only three types of questions possible, numerical questions possible in this chapter. You can summarize all three of these as an interplay between concentration and K or Q. That's all that's going on. The first two are very easy. Let's take a look. Let's go back to our favorite equation. N2 plus 3H2 is in equilibrium with 2NH3. Suppose I tell you that this is 0.5 molars, this is 0.3 molars, and this is 0.2 molars. Some values, calculate Q, QC. Plug it in. QC equals, what do we have? You tell me. It's products over reactants, coefficients become powers. 0.2 squared, good. Let's write down in terms of the species first. Yeah, and what goes on the bottom? Mm-hmm. And so NH3 is 0.2 squared, N2 is 0.5, and H2 is 0.3 cubed, whatever that comes out to. No units. Both reaction quotient and constants do not have units. Even though you might be tempted, it's molar square, molar cubed. No. No units. No. Excellent question. Yeah, common source of confusion. The K value here is reaction constant, deals with equilibrium. The K value we found last time was rate constant, deals with how fast a reaction takes place. Same symbol, two different things. Not the same. I think this K is uppercase, and that K was lowercase. That's the best they could do. Okay, cool. Same thing here. I can have N2 plus 3H2, 2NH3, and suppose I tell you, I specify that at equilibrium, I measure this to be 2 atm, this to be 3 atm, and this to be 1 atm. Pressures, calculate Kp. One square, reactants, nitrogen 2 to the power of 1, hydrogen 3 to the power of 3. Right? Same deal. Another easy one is, I'll take out one of them, one's missing, and I tell you that the Q value is, I don't know, 50. Calculate the concentration at that instant of hydrogen. What do you do here? So I took out one of, you have concentrations given to you, but one of the concentrations is missing. But I've given you Q. Yes. Exactly. So it's just the same equation, but different parts are missing this time. Q equals, let me rewrite this. This time I've given you the left-hand side. NH3 is 0.2 squared, N2 is 0.5 to the power of 1, unknown, so x to the power of 3. Solve for x. Something. Right? And you can repeat an example here. You know some of the equilibrium concentrations, but one is missing, but you know the K value. Plug and chug, solve for the unknown. Okay. Any questions? Cool. All right. The first two are easy. Let's tackle the last one here, where you're given the K value and initial concentrations, but you're trying to figure out the equilibrium concentration. This is the most important question because equilibrium, well, where does the equilibrium lie? Where's the sweet spot? What are the exact values of each of the concentrations or pressures when a chemical system reaches equilibrium? So that's this question. All right. Let's say we have N2, H2, and 2NH3. 3. Suppose I tell you that the K value is, well, you know what? Let me do a different question this time. Carbon plus oxygen gives carbon dioxide. Suppose the K value is 100. Right? So this is the question. I've given you the K value, and I've given you the initial concentrations. Let's say this was 1, this was 1, or this was 1, this was 2, and this was 0. Okay? We want to calculate, so that's I for initial. We want to calculate what these numbers are at equilibrium. Obviously, they're going to change, right? These two numbers are going to drop a little bit because they're reactants and there are no products to begin with. So the reaction is going to go forward a little bit, but you don't have to worry about that. Just saying, like intuitively, these numbers will come out to be a little lower, this will come out to be a little higher. Don't know what those exact numbers are. But to help us with bookkeeping, you might think that there's 3 variables to solve, right? Because there's 3 concentrations that are unknown. No, there's only 1 variable to solve, thanks to stoichiometry. Because if I know how C changes, then I also know how oxygen changes and how carbon dioxide changes. Because stoichiometry, everything, all reactions proceed in a very rigid ratio, right? If I use 5 carbons, I have to use 5 oxygens to get 5 carbon dioxide. There is no other way. So because of that rigidity provided by stoichiometry, we only have 1 variable to solve. That bookkeeping is C, change. So we're going to always, for equilibrium questions of this kind, draw what's called an ICE table, ICE, initial, change, equilibrium. This is just a bookkeeping tool. What goes in the change is the unknown amount of change that happens as the reaction goes from initial to equilibrium. How much does it change by? I don't know, so it will have variables in it. But suppose carbon changes by X molarities. Then oxygen must also change by X molarities. And what I like to do is, for reactants, always put negatives. Minus X plus X. So far, so good? So take this home. For ICE tables, reactants always get negatives, products always get positives. Even if the equilibrium is in the backwards direction, that's no problem. Because when you solve for X, X can have both positive and negative values. Right? The reason why I'm putting negatives and positive here is because I'm assuming the reaction is going in the forward direction. So reactants are going to get consumed, products are going to form. But that may not be the case in some other question. Maybe the equilibrium lies behind. So maybe these will add up and these will subtract. That's okay. Because if that's the case, when you solve for X, you'll get a negative value. At least 1 negative value. Okay? We'll do all of that in a second. Okay, now suppose this had a coefficient of 3. In keeping with stoichiometry, this would become plus 3x. Okay? So that's how you come up with the change row. If this was 4, this would be minus 4x. Just copy down the coefficient. That will give you the right amount of ratios. But since that's not the case, let's work with minus x, and plus x. Equilibrium is just the resultant amount. We started with 1, it got reduced by x, so equilibrium is simply take your initial, add the change, and you'll get equilibrium. So this would be 1 minus x, 2 minus x, 0 plus x is just x. Great. So we know what the equilibrium concentrations are. Those can go in K, right? Because K accepts equilibrium concentrations. K is given to be 100. How do I write K? Products over reactants. So concentration of CO2 divided by concentration of carbon times concentration of oxygen equals 100. CO2 here is X. Carbon is 1 minus X. Oxygen is 2 minus X. Equals 100. Now solve for X. It's messy, it's quadratic, but that's all there is to it.
And so if there were coefficients, would you put them as powers?
Yep. The coefficients would come here in the change row. They would be reflected in the change row and also in the powers. We'll do a question with that in a second. Okay, let's do that quadratic real quick. So we have multiplying both sides by the first denominator. We would have 100 times 1 minus x, 2 minus x. I'm going to multiply these two first. That's 2. 1 times 2 is 2. 1 times minus x, minus 2x plus x squared equals x. So what is that? 200 minus x minus 2x is minus 3x minus 300x plus 100x squared. Subtract x from both sides, so this becomes 301. Plug all of that information into the quadratic formula, and you're done. This is a quadratic, right? Quadratics have how many solutions? Right? They could have up to 2 solutions. So suppose, I'm not going to solve this, but suppose you solve this and you got 2 values. Let's say that the first value that you got was positive and the second value that you got was negative. How do you choose which one's the correct x? Easy. Take each of your x values and plug them into the final equilibrium row. Can molarities be negative? Nope. So whichever x value gives you negative molarities, that can't be the case. That can't be the one. So if I have positive molarities, that could be positive, and this are all positive. But if I have a negative x, this is fine because this will give you a positive. This is also fine, but this becomes negative. You get a negative number for carbon dioxide's equilibrium molarity. That's a problem. So you lose that one. So the correct x value is the other one. Yeah.
So it can never be the case to use a negative.
No, that's no. So for example, you can also, because sometimes your quadratic will give you 2 positive values. So I'll give you an example. Suppose you got 0.5 and 1.2. What do you do then? If I put 0.5 here, 1 minus 0.5 is 0.5, positive. 2 minus 0.5, also positive. 0.5, also positive. That's good. But look at 1.2. It makes this one negative. 1 minus 1.2 would be negative 0.2. That's a problem. So you always want to do this manual check. There's no clean way of, yeah. One quick note before we proceed is that remember QP versus QC, depending on what you're using to measure the abundance of the species, and KP versus KC, they're both related to each other very simply as follows. I can never remember the order. Hold on, let me check. But I think it is K. Is it KP equals? Oh no, that is correct, but that's not the equation. Here, that's ideal gas law. I think it's QP equals RT to the power of delta N QC. I can check if this is correct in a second. KC. Yeah, check your, like down in the lecture when this is discussed, just one of them is P, one of them is C. Check which one it is. It doesn't matter. All you need to know is what this delta N part is. Delta N simply means moles of gas, products minus reactants. So you're subtracting the moles of gas, products minus reactants. It's a good example. Yeah, total. Total on the product minus total on the reactant side. A good example is, H2 gas plus O2 gas is in equilibrium with H2O liquid. What is delta N going to be in this case? Products minus reactants. Any gas on the product side? None. It's all liquid, so 0. Minus any gas on the reactant side? Yes, 2 plus 1. So delta N in this case would be -3. Right? Your moles are just the coefficients. It's not given mass over molar mass. No. Just that. Stoichiometric moles. There's got to be a better one. Oh yes. Let me give you an explosive. Because what's an explosive? It's a solid or liquid whose products are almost entirely gases. That's an explosive in a nutshell. Why? Solids and liquids have very little volume. Gases have a lot of volume. So any reaction that leads only to gaseous products, that's pretty much an explosive. Or a fuel, one or the other. Ammonium nitrate. Don't need the parentheses. Ammonium nitrate, if you make it explode, becomes, I think, nitrogen. Let's just pretend that you get nitrogen, hydrogen, and no, you get nitrogen and water. Let's balance this real quick. Nitrogen is fine. Hydrogen is not fine. And I think you also get some oxygen. So hydrogens are fine. Oxygen, that's 3 oxygens. Does that make sense? Balanced? And so if I balance it fully, I get 2NH4NO3, multiplying both sides by that 2 to get rid of that denominator. Can you check if this is balanced? Yeah? Balanced, right? Okay. This is solid. You don't need to memorize these. These physical states will be given to you in a question. But suppose these were the physical states. So what would delta N be here? Gases on the product side minus gases on the reactant side. 7. So how many? Yeah. 2, skip the liquid. 1, that's 3, minus none on the reactant side because it's all solid, so delta N is 3. Right, just a little topic. That's interconverting between the two. Great. Not
Which one were you not sure about?
whether it's Kp equals stuff times Q, Kp equals stuff times Kc, or Kc equals stuff times Kp. Yeah, it's one or the other. Okay. Another fine note is if you have Qc or Kc, you can only input the molarities of species that are in aqueous state or gaseous state. Nothing else. Solids and liquids don't enter the expression. I'll give you examples to illustrate that. And for the pressure part, only pressure. Well, liquids don't have pressure, solids don't have pressure, so the only thing that makes sense to talk about pressure is gases. Pressure of only. Important thing to remember is that in both cases you skip liquids and solids. They never enter the equilibrium expression. Yep. Skip all the products, skip all the reactants that are liquids or solids. So let me make up a good one. Oh yes, glucose. C6H12O6 plus, if you burn glucose, you get carbon dioxide and water. You get 6. That's good. There's 6 oxygens already. There's 12. 6. Glucose, as you know, is solid. Oxygen is a gas. Carbon dioxide is a gas. When water is produced, it's hot, it's steam, so also a gas. You don't need to remember this, like I said. This will be provided to you in a question. Great, so let's write down the Kc or Qc expression. Kc or Qc expression. What products are going to go in here? Yep. Both of them go because this is concentration. Gases can have concentration, and aqueous things can have concentration. This is actually, let's say, this is not a good example, but yes. So this would be CO2 to the power of 6, H2O to the power of 6, and that's solid, so I skip oxygen to the power of 6. And similarly, if I had QP or KP, then same thing. Only gases enter. 6 oxygen to the power of 6. You skip the solids and the liquids. Yes? Here, H2O, I've given you as gas. Yeah. If I had given it to you as liquid, then no. There exist both cases. If your reaction is really hot, the water that's produced is produced as steam. If your reaction is cold, like acid-base reactions, then it's liquid water that's produced. One more, NaCl, solid, breaks up into Na plus, aqueous, and Cl minus, also aqueous. Tell me what Kc here would look like. Na plus to the power of 1, Cl minus, power of 1. That's it, right? Is Qp or Kp applicable here? Nope. No gases. This is dissolution, right? This is an example of a dissolution reaction where something is dissolving. You don't need to write this down, but this is sort of a preview into the next chapter. This is a dissolution reaction. Look at what's happening here. You always dissolve a solid and produce its ions, or produce the dissolved version of it. So it's only the products that enter. The reactant never enters in dissolution reaction because they're always solid. And so QC and Kc is always a product for dissolution reactions. That's why it has a special name. It's called KSP, solubility product. Okay, coming up, next chapter. But yeah, all of this is related. All right, now let's do some more equilibrium questions. And then there's one little topic, and then we're done. Can someone tell me what time it is? 10:58. Okay, 20 minutes. Pretty good. Let's do one more. Okay. Nitrogen plus oxygen gives, let's say, NO2. 2, 2, and 2. X squared. X times. Let's just do NO. 2 times NO. Yeah, that's good enough. All right, I tell you that the K value is I don't know, 10, and I give you these initial values. I say that this is 5, this is 4, and this is 10. These are pressures, so we're going to do a pressure question. Okay, these are the initial values that have been given to you. They're an ATM. And I've told you that K equals 10. Same question, calculate equilibrium pressures. Let's draw an ice table, ICE. All right, now in terms of x's, tell me what do I put here? Negative x, positive 2x because it has coefficient. Good. So equilibrium is just the sum, 5 minus x, 4 minus x, 10 plus 2x. So far so good? Great. Let's write down the expression. What goes on top? NO, because that's the product, which is 10 plus 2x. Square. What goes on the bottom? Yep. The reactants 5 minus x and 4 minus x. This is equals 10. Quadratic again. Solve for it. By the way, just solving for x is not the answer. Once you solve for x, question will be framed like this. Calculate the equilibrium concentration of NO. So you solve for x and then you plug it in here to calculate its value. Right? So that's plug it in to figure out the constant. In this case, pressure. Okay. No new chemistry, one new mathematical trick. Small x approximation. Here's an obvious problem that you could encounter. This is a quadratic, right? Is quadratic the maximum that it can be? No, right? Remember our glucose question? We had 6 powers, right? To the power of 6, to the power of 6, maybe even to the power of 12 somewhere when you combine them. You don't know how to do sextet questions, or I don't know what, dodeca, whatever, 12th order questions, right? You have learned how to solve linear equations and quadratic ones, maybe cubic, easy ones. But you have no idea how to do order 6 equations. So when something like that happens, you can use a nice mathematical trick called small x approximation. It's very easy. And you only use this when k is very small. That's the only time you can use this. How small is very small? Great question. Let's say 10 to the negative 3 or smaller. But if you are close to 10 to the negative 3, you should be uncomfortable, and there is a test that you can use to make sure that you're in range, called the 5% test. Okay, so let's do a question with that. Lucky for us, this is actually very nice because most chemical reactions in the world either have very small k values or very large k values. Here's something I forgot to discuss. If you have a reaction and it has a certain k value, if I flip it, if I make the reactants products reactants, what do you think happens to its k value? K is products over reactants, but the products and reactants have interchanged because it flipped the reaction. So your k value becomes inverse, 1 over k. Okay? So if one direction has equilibrium constant k, then the reverse direction has equilibrium constant 1 over k. Now, remember I said there's 2 main types of equations in the world, very big K, very small k. Small k, this handles. If you have a very big k value, flip the reaction. the constant becomes 1 over. What's 1 over a very big value? Very small value. So even though there exists very big value case, you can always convert them into a small x approximation case by flipping the chemical reaction. All right, let's do this question real quick. Let's go back to the glucose one. C612O6 reacts with oxygen 6 to give 6 carbon dioxides and 6 waters. Let's say this is gas, also gas, also gas, and this is solid. And I tell you that the concentrations here, we start with, so I give you 3 here, 4 here, and 1 here. These are the initial values that I've given. Anytime in a question you're not given the initial value of a certain species, you should assume it's 0. Missing? 0. Yeah? And we don't even care about this because that's the solid species. Just cross out the solid and the liquid parts. Great. C and E. What's the C here? What x term goes here? Negative 6x, good. And here? Yep, positive 6x, coefficient is 6, and here also 6x. So add them up, 3 minus 6x, 4 plus 6x, and 1 plus 6x. Awesome. And I tell you that the k value, this is part of the question, is 2 times 10 to the negative 7. Small? Pretty small. Okay, let's set this up. Products on top, 4 plus 6x, that's a product, to the power of 6. 1 plus 6x, that's also a product, to the power of 6, divided by 3 minus 6x, let me make one more change. Let me make this 1 a 0, okay? So at equilibrium you have 6x. Just make a change that 1 to a 0. Okay? Great, so H2O just becomes 6x to the power of 6, 3 minus 6x, great. Equals k value, which is given to be 2 times 10 to the negative 7. Pretty small, so we'll do small x approximation. Just very straightforward. If you have an x term that's being added or subtracted, drop it. That's the small x approximation. If you have an x term that's being added or subtracted, drop it. Yeah.
Isn't it 3 minus 6x to the 6?
Yes, to the 6. Good. Thank you. I was missing the 6 from the coefficient of oxygen. Okay. So what gets dropped? Anything that gets any x term that is added or subtracted. There. Is that added or subtracted? Yes, it's being added. That 6x goes away. Added or subtracted? Subtracted goes away. Is this 6x added or subtracted to anything? No. That is a standalone term. It's not being added or subtracted, so that gets left alone. And as a result, the equation becomes much nicer to handle. Let's rewrite this with the terms dropped. What remains in this term? 4 to the power of 6. What remains here? 6x to the power of 6. 3 to the power of 6 equals 2 times 10 to the negative 7. You still have a 6th order term, but that's easy. It's only a single term that's 6th order. We know how to do that. Let's send all the numbers over. So you have 6x to the power of 6 be 2 times 10 to the negative 7 times 3 to the 6 divided by 4 to the 6. So far, so good? Yeah? What's the last thing I should do to get rid of this 6? Square root would be if I had a square here. You're good. Log is an option, but a simpler way is literally what's the literal inverse of 6 to the power of 6? Sixth root, yes. Square root would be for 2. Yes. You're good. Take the sixth root of both sides. Let's say you get some answer. Solve for x. It's that number divided by 6. While you copy that, I'm just going to write down a couple more things here. Yes.
So basically what you're saying is that if you plug in that x value into the initial concentration, like that's close enough.
Yep, close enough. And how do you test whether it's close enough? I'll tell you in a second. But just for more practice, what terms get dropped here in this expression? Let's use small x approximation. Does this get dropped? This? Yep. What about that? Yep. What about that? Yep. So what do we end up with? 2x squared, 10 to the power of 3, 4, and 4. Okay. And here's how you test whether what you've done is valid or not. Last thing, 5% test. Okay, 5% test is very simple. Take your x value that you found, divide it by the smallest initial value, and times it 100, and see if you get less than 5%. If you get less than 5%, what you did was valid. If not, then what you did was invalid. Smallest initial value. So pretend that the x that we found here was 10 to the negative 7. I don't know, some number we found. Suppose it was 10 to the negative 7. Let's say 3 times 10 to the negative 7. That's the x value we found here. So the 5% test would be 3 times 10 to the negative 7, which is the x value that we found, divided by the smallest initial value. Which of these has the smallest initial value? Anywhere, products or reactants? 3, right? Look at all the initial values, pick up the smallest one, 3. That goes in the denominator, times this by 100. If you get a number, if you get an answer to this that's less than 5, you're good. If it's more than 5, then your small x approximation was invalid. So the small x approximation is all the way at the end. Yes? Say that again? If it's invalid, the question will be engineered in such a way that all it will ask for you is, you can't do it. For example, in ALEX, a question that they ask is, they'll give you the k value, they'll give you the initial data, and then they'll say, what's the equilibrium concentration? They'll give you a couple sample values, and then one option will say, can determine. So you choose can determine. Okay? Any questions? All right. I think we're out of time, are we? 5 minutes. I'll squeeze that last topic in now. It's very, very, very simple. I'm doing this because even if this, seemed fast-paced, don't worry. You'll do the same thing over and over again in the next 2 chapters. So it will become second nature. But I want to go through this last topic real quick, which is you should think of this topic as messing with already established equilibrium. Right? Suppose we take a chemical system, we make it go to equilibrium. So an equilibrium has been established. Now you disturb that equilibrium via an external change. And what you're being asked is, where's the new equilibrium? Is it to the right of this already established equilibrium, or is it to the left? Okay, that's all this topic is, and it's very simple. The mantra, which is this guy's principle, is that the reaction does the opposite of external change. The reaction does the opposite of the external change. Makes sense, right? Equilibrium is where the reaction is happy. That's where it wants to be. If you disturb it, it will do everything in its power to come back to that same place. That's the observation. Okay, this is the only question that's asked of this topic. Let me make this up. N2. Suppose you have a chemical reaction, and I'll give you a bunch of things about this reaction. All of these are gases. I'll say that the delta H is negative 100. And here's a series of questions. Temperature is increased. Concentration of NH3 is increased. Pressure is increased or decreased. And D, inert gas is added. E, what else do we have? Temperature's increased, blah, blah, blah. Oh, catalyst is added. Okay? Give me, yeah. Inert gas, yeah. Inert gas as in, I'll tell you what it is. Okay? Last question, promise. Okay, so understand the question. Here's a chemical reaction. Here's a bunch of information that's given to you about this. An equilibrium has already been established. Think of this reaction already at equilibrium. What we are being asked here is, if the temperature is suddenly increased, that would disturb the equilibrium. How would it disturb it? Would it move would the new equilibrium be to the right or to the left? That's all we're being asked. Okay. This is how you do it. Let's start with B. NH3 is increased. NH3 is increased, right? So everything that's given to you in the question is an external change. The reaction's response will be exactly the opposite. That's this guy's principle. So if the NH3 amount is increased, what will the reaction do? It will try and decrease it. And it will move in a direction either this way or that way that corresponds to decreasing NH3. So let's think about it. Since the external change is increase in NH3, We want to decrease NH3. Which way does NH3 decrease in? Going this way or going that way? Going to the left, right? Because if you go this way, this is the product. If you go that way, it's a reactant. Reactants go down over time. So direction of shift would be to the left.
That's for the concentration.
B, yeah, this is part B. Let's go to part A. Temperature is increased. The reaction will try and decrease the temperature. Well, how do we know which way the temperature goes up or down? Easy. Delta H is negative. Remember what delta H tells you? Whether the reaction is exothermic or endothermic. A negative value corresponds to which one? Exothermic. Exothermic is increase in temperature. So what this is saying is that going to the right, your temperature increases because the reaction is exothermic, which means going to the left would decrease your temperature. External change, temperature is increased. Reaction will respond by decreasing temperature, which happens if you move to the left. So the direction would be, basically what I'm saying is that the reaction's response determines the direction. Okay. Next up, pressure. Pressure is decreased. To determine pressure, pressure is determined only by the gaseous components. How many total moles of gas do we have on this side? 4. How many on this side? 2. The side that has the more number of moles of gas is the high pressure side, and this is the low pressure side. Pressure is decreased. Reaction will try and increase pressure, which is what direction? You want to move towards the high pressure. Good. Left again. Inert gas is added is the same as saying pressure is increased. These are the same thing. If you add a gas that's not involved in this reaction, all it will do is increase the overall pressure. So if the pressure is increased, reaction will try and decrease pressure, which means it will try and move towards the low pressure side. That's over there. And the last thing that you need to know is catalyst is only relevant to how fast equilibrium is achieved. It doesn't change the equilibrium, right? Catalyst only speeds up the reaction. So it will get you to that equilibrium faster, but it will not change where the equilibrium is. So if catalyst is added, no change, no change. Reaction, the equilibrium remains as is. And that's the end of chapter 13.